Greetings and welcome to another installment of Quan Slob. This is 33 in our basic application series, and this time around we're going to power on with part 5 of our exciting summarizing data series. But before we get underway, let's take a look at our previous Ye Oldie Quan Slob challenge. Two-parter. First part, are there any potential outliers in our collection of 6 numerical values here? 1, 2, 3, 4, 5, and 21. Well, one very direct way to get to an answer is to calculate our IQR, our interquartile range, which is Q3, our third quartile, minus Q1, our first quartile. 5 minus 2 is 3. Then we can calculate our potential outliers' lower and upper boundaries. We'll just hash through the math here. The lower boundary is Q1 minus 1.5 times our IQR. The upper boundary is Q3 plus 1.5 times our IQR. 1.5 times our IQR is 4.5. 2, our first quartile, minus 4.5 is negative 2.5. 5, our third quartile, plus 4.5 is 9.5. And so we'll first dutifully complete our little summary stats table here and simply observe that 21 is not contained in the interval negative 2.5 to 9.5. It is therefore a potential outlier. Part 2. Suppose we create a new numerical attribute by dividing x, our original collection of 6 numbers, by 1,000. Well, we can simply repeat the familiar ritual of creating our summary stats table and observe that 0.021 is greater than our upper potential outlier boundary of 0.0095. It turns out that multiplying or dividing numbers by any constant value, so long as that value is not 0 or infinite, will never change the outlier status of any value. Well, how do we know this? Well, there's a pretty interesting and telling way of illustrating this. So what we're going to do is we're going to place our boundary interval along with our value of 21 on the number line here. Now, when we multiply our collection of numbers by a positive number that's smaller than 1, it's like we're compressing or shrinking our domain. When we multiply by a number that's greater than 1, it's like we're stretching out or expanding our domain. Now, when we multiply by a negative number, it's like we're flipping our domain, like a mirror image. Notice that under these transformations, our outlier can never enter the interval, nor, for that matter, can any point in the interval ever exit it. Scaling our attribute by division or multiplication cannot change the potential outlier status of our transformed values, so long as we don't scale by 0, infinity, or negative infinity. Okay, moving on. So let's make us a box plot. What do you say? Okay, so this is going to be a horizontal box plot here, and we're going to start by drawing the plotting region, the rectangle here. We're going to place our x-axis just underneath the plotting region here. Now, we need to make sure that our x-axis contains our domain of values. So we're going to go from negative 5 to 25 and place ticks here at intervals of 5. Okay, let's start by drawing a sort of thick vertical line segment at the median value, Q2. That value is 3.5 here. We're going to next draw a slightly thinner vertical line segment at Q1. That's a value of 2 here. And another at Q3. That's a value of 5. Now we can complete the box by drawing the edges, the top and the bottom, on a horizontal box plot. And so this here is our box, our fabled box from a box plot. Okay, so now moving on. The lower whisker is a shorter segment that is drawn at the smallest value of our numerical attribute that is not a potential outlier. 1 is our minimum value. It is not a potential outlier. Draw a whisker there. Analogously, the upper whisker is drawn at the largest value that is not a potential outlier. Now, 21, our maximum value, is a potential outlier, so that means we need to draw our upper whisker at 5 here. But notice 5 is our third quartile, and there's already a segment we've drawn here at the top of the box, top of our box. So in this case, we don't draw our whisker. And even if we did, it's not going to affect, cosmetically anyway, the appearance of our plot. So now let's connect our lower whisker to the box here, just a thin segment. Okay, our last order of business as far as the plotting region goes is to indicate our potential outliers. And here we have one, namely the value of 21. So I say we indicate this with a little circle, and we can also use a filled little circle or a star or an asterisk, pretty common. And there we have it. Pretty sweet, huh? One last thing. Let's define the so-called figure region and give it a title. As someone looking at it will have a little context. So now we know the ingredients of a box plot. So I say we use what we know to examine a box plot not of our creation. Start speed in miles per hour of Major League Baseball pitches from our earlier data set. Very first thing I want to point out here is that when we look at a categorical attribute, we can treat unrecorded or missing values as a category. But with a numerical attribute, we can't do this. So instead, we simply remove pitches from our data where the start speed was not recorded. And you can see here that we have a little under 6 million pitches whose start speed is available and recorded in our data. The other thing is that with a numerical attribute, this particular numerical attribute has been recorded to a precision of tenths. So we have values like 83.1, 92.8, for example. So our domain is pretty crowded. And it also means that a box plot like we have here is a pretty good way to visually express our distribution. Box plot is a graphical way to show a distribution. And a distribution conveys what? Popularity of values. That's what a distribution is all about. So we can interpret this by sort of backwards engineering this plot based on what we know. Now the graph here, you can see, may not tell us the exact values of these statistics, but we can use this plot to visually approximate the values by looking at the x-axis. Q2, the second quartile, the median, is the heavy segment inside the box. Just learned that. Looking at this graph, Q2 is maybe, what do you say, like a smidge less than 90, call it 89.5. Q1, maybe 84 about. Q3 looks to be about 93 miles per hour. Minimum, I'm going to guess 45 miles per hour. Maximum here out to the far right, about 105 miles per hour. Q2 is the value that splits our list of sorted values in half. Q1 splits the lower half into half. Q3 splits the upper half into half. So let's contextualize our interpretation here. Of our almost 6 million pitches in our data set where start speed, velocity leaving the pitcher's hand, was recorded, very close to half were slower than 89.5 miles per hour. About 3/4 were faster than 84 miles per hour. About half were between 84 and 93 miles per hour between Q1 and Q3. The slowest was very close to, I'd say, about 45 miles per hour, and the fastest pitch was recorded at a velocity very close to 105 miles per hour. Now, another very popular graphical way to convey the popularity of values is the histogram, okay? So what we're going to do is we're going to borrow the same x-axis from our box plot here. Now, a histogram divides the domain into contiguous bins, each bin of equal width. So let's place the left edge of the leftmost bin at 40 and the right edge of this bin at 42. This bin has a width now of 2, has a width of 2 miles per hour. Notice something very important here. Since the bins along our domain have equal width and since they are contiguous against each other, the decision of where to place the two edges of any one bin determines the location of all the other bins. So our histogram now places a bar over each bin. The height of the bar indicates the popularity of values within each bin. In this example, we use the familiar frequency to express popularity. With a histogram, there are two other ways by which we may quantify popularity. One is relative frequency. Now here, see, the height of the bar tells us the percent of the total number of observations that are contained within each bin. The other is to quantify popularity as density. Same concept of density that one might encounter when dealing with continuous distributions, by the way. Now here, the quantification of popularity is such that if we sum up the area of all the bars, they're all rectangles, of course, the sum will be 1. Now, showing here, this is pretty loose notation, but what we're saying is that each bar is a rectangle and has an area. The sum of all these rectangular areas is 1. Now, you may be thinking a histogram looks similar to a bar chart. The first distinction is that with a bar chart, the bars are drawn over discrete categories. Here, our domain is numerical. Our bars are drawn over a portion of the number line. The other distinction, very importantly, is that the bars on a histogram are adjacent. They're contiguous, abutted against each other, whereas the bars on a bar chart have a little space or gap between them. Now, this is an admittedly light touch look at histograms. The width and location of bins is often handled automatically by the software that we use to render it, or someone used to render it. When we have a crowded domain, that is, our numerical attribute is highly granular or continuous-like, and we have many observations, like here we have well over 1 million, almost 6 million, the choice of bin locations usually doesn't have much impact on the overall shape of the histogram. So you can see here, just to illustrate, we've narrowed the bin width to 1, and the overall shape looks about the same. On the other hand, when we have a small number of values of a highly discrete numerical attribute, the choice of bin location and width can have sometimes, just to note, a pretty dramatic effect on the shape of the histogram. So, must all the bins have the same width? Well, technically, no. Now, when expressing popularity as a density, and only when expressing popularity as a density, every rare once in a while we may encounter a histogram with unequal bin intervals, and this does not at all change the interpretation. The areas of the bars still sum to 1. But if we're producing the histogram, I would advise against this sort of funny business. Just keep the bins of equal width. So what happens if a value lands directly on top of the edge between two bins? Well, the software will impose some sort of rule, like they call it place left or fall left, in which case the observation will be placed in the bin to the left, or analogously fall to the right into the right bin. Okay, so now before we close out, time for our super futuristic Quant Slob challenge. So here we go. How might we describe the shape of this distribution, the shape of the shaded area? Seems simple enough. Or are it? We're to take a look at this along with lots more exciting stuff upcoming in part 6. You are definitely not going to want to miss that. And that's it. That's going to do it this time around. Thank you very much for tuning in. Don't forget to stay tuned for more Quan Slob.